I'll be talking about a way to verify liveness and temporal properties of infinite state systems with infinite state per node and dynamically spawning of threads and nodes. And quite surprisingly, it's all done in first order logic without reasoning about set cardinalities or arithmetic. So if you've thought that first order logic is not powerful enough to verify these kinds of interesting properties, come to my talk and see differently.
Actually, I think the order is wrong. Is that you? Okay. All right.
Hello, everyone. My talk is at 11:20 a.m. at Bunker Hill, and I'm going to talk about a compositional reasoning technique and an inference technique for weakly isolated transactions. So this is basically a story of how we applied PL techniques to solve a real problem in databases. So we in PL community tend to think serializability as the be-all and end-all correctness criterion. But in databases, most often they are not really assets. So they are not, the transactions are not really serializable. There are multiple levels of isolation which are difficult to reason about. So this talk focuses on how we used PL techniques like relay guarantee to reason about these transactions. And I also talk about an automated verification technique that scales to real database benchmarks like TPCC and TPCE. Thank you very much.
Hi, so at 11:45 today, I'll talk about programming and proving with distributed protocols using a separation logic we're calling Diesel for distributed separation logic. So the way that people verify distributed systems these days typically emphasizes verifying these big chunks of infrastructure as monolithic things, and then you put them on the shelf and you look at them and you're happy that you did it. But it's very difficult to reuse those results to build applications. So we're looking at techniques from from separation logic and applying them to distributed systems to reuse these infrastructure, pieces of verified infrastructure to build applications. So I've put a couple of cartoon rules on the slide here. These are the flavor of things that we're doing, and you can check us out at distributedcomponents.net. Thanks.
Hi everyone, my talk is the first one on the other room. I'm going to present what we believe is the first type inference engine for C, one that is capable of dealing with C intricacies and allows you to reconstruct a partial C source code into a complete well-typed program, not free from undefined behaviors though. In order to solve this problem, we need to look into certain challenges like those I'm showing you in that slide, syntax ambiguities, semantic ambiguities, and so on. So if you would like to learn more, I welcome you to the talk. Thank you.
Hi, hello. I'm Annabelle McIver. I'm going to be talking at Bunker Hill just after lunch. I'm going to be telling you about a new proof rule to prove termination for probabilistic programs. It uses a variation of the variant rule adapted with progress conditions, and it's adapted to make sure that there are no weird Zeno effects which can occur in infinite state probabilistic programs. So I'll tell you all about how all of that works out. I just want to say that these famous people have nothing to do with probabilistic programs, but they look pretty cool on this slide, which I adapted. But I'm really not going to be talking about washing systems. It's probabilistic systems. Thanks very much.
Hi. So the first afternoon session in Bunker Hill will be quite rich on results on probabilistic termination. And what we do in our work is that we basically generalize lexicographic ranking functions to probabilistic programs. So in classical non-probabilistic program analysis, lexicographic termination proofs provide a very strong and efficiently automated proof rule, and we would like to leverage this to the probabilistic setting. So if you would like to know what is a probabilistic analog of a lexicographic ranking function, what are the intricacies of showing that these lexicographic termination proofs work for probabilistic programs, and how does this all fit into the general picture of proving termination of probabilistic programs, then you're welcome to join us at 2:05 at Bunker Hill.
Hello, everyone. My talk is about termination analysis of quantum programs, and this is the third talk in the termination session. And in my talk, actually in the previous work, we noticed that the termination of a quantum program is equivalent to the existence of some quantum ranking function. But at that time, it is really difficult to generate this ranking function because the mathematical form is bad. And now in this work, we find a very good definition, a mathematical concept we call the linear ranking supermartingale to check the termination of quantum programs. And this is actually a quantum generalization of the ranking supermartingale for probabilistic programs. And the most importantly, we can using a semi-definite program to generate such a linear ranking supermartingale. And actually, I noticed that this might be the only talk about quantum programming in POPL. And so I will give a full introduction to some basic ideas. So everyone is welcome. Thank you.
So ours is the last talk of the post-lunch session at Bunker Hill. This is the odd man out of the session. The session is called Termination Analysis. The talk is not about termination analysis at all. The talk is about cost analysis of programs. So cost analysis is basically establishing lower and upper bounds on on some abstract notion of execution time of the program. And what we are trying to build here are very expressive proof systems for doing this. In particular, we are interested in combining cost analysis with functional verification. What we basically show is that you can use very basic techniques, higher order refinements, and monads to do this. So if these topics interest you, please show up. 255 Bunker Hill. Thanks.
So we all know how to verify data structures compositionally. The magic sauce is separation logic. And in separation logic, the way you describe an unbounded data structure is with an inductive or recursive definition. For instance, a list is an element and another list. But when you have like concurrent data structures like this mess on the slide, you can't do this kind of thing easily because you have overlays like the red and blue lists arbitrarily overlap. You have sharing like the node 6, and you have arbitrary traversals by the different threads. They just walk around in random ways. So how do you reason about these kinds of data structures compositionally? Well, come to the first talk after lunch at Watercourt, and I'll tell you. Thank you.
Hi, so I want to tell you this afternoon about System F interacting with untyped languages. So specifically, two problem domains. So one is how can you enforce parametricity by encryption, by sealing primitives. And the second is a gradually typed extension for System F, for which there's a lot of references, which is about the polymorphic blame calculus. So the results I want to tell you about is first that we disprove an old conjecture by Sumi and Pierce. So we prove that the sealing compiler is not actually secure. Secondly, we argue that there's an additional correctness criterion needed for gradual typing. So it should preserve reasoning about source programs, not just safety, about typed programs, sorry, not just safety. And we show that the polymorphic blame calculus doesn't do this. So additionally, I will tell you what all of this has to do with something I call universal types and what all of this means for the parametricity that has recently been proven for the polymorphic blame calculus. Okay, so thanks.
Hi. The title of my paper is Symbolic Types for Lenient Symbolic Execution, and I'd like to say three things about it. First, the word lenient in our title refers to computation in Rosette, which is a language for writing programs that use a solver. Rosette symbolically executes a program to compile it to solver constraints, but it also allows programmers to mix in concrete features and concrete code, which enables more use cases, like in this example here. If you can read it, it's a function that converts polar coordinates to rectangular coordinates, and the first argument is symbolic, but the second argument, we require it to be concrete to avoid symbolically executing sine and cosine, which is hard. Number two, one potential problem with mixing concrete and symbolic code in this way is it can be hard to debug. So here, in the example, I'm asking the solver to find the point at the origin, but I've accidentally switched the order of the concrete and symbolic arguments, and so the solver has returned unsat. And so number three, in my talk, I'm going to present typed Rosette, which helps programmers automatically use symbolic values properly with a type system. And so instead of unsat, which is unhelpful, you get a nicer type error message. Thanks.
Hello. This is about bidirectional programming, about programming lenses. And what's interesting about bidirectional programming is that, well, lenses are, well, they have two directions to specify. We want just to write one program to specify the behavior of both directions. And, but writing just one program doesn't mean that the task has become just unidirectional programming. Because in fact, in a lot of languages, we have to switch between the get and put interpretations of the program to actually specify both behavior. But actually, we do have a way to program lenses unidirectionally, and we're going to explain how to do that in terms of whole triples, in fact, two kinds of triples. So come in the afternoon for the whole story. Thank you.
Hello. It's whether type classes in Haskell or traits in Rust or implicits in Scala, these are all increasingly important ways to structure your program. And that's no wonder, because if you look at it the right way, they are essentially the canonical way to abstract over context, and that's a rather big deal. So in this talk, I'm going to present implicit function types, which make implicits even nicer to use and even more powerful way to use them. And furthermore, they have a really simple foundation. It's the last talk in Waterford this afternoon.
Right. Bisimilarity is the term that stands for a certain kind of equivalence between, for instance, processes. And up-to techniques are used to make it easier to prove that two things are bisimilar. Now, if you define bisimilarity using co-induction and size types, then it turns out that the class of up-to techniques falls out naturally. And in my presentation later today, I'm going to try to explain what I mean by that.
This is not my slide. Since it's missing, I will just talk. So basically, our work is we propose a closed form solution for cache behavior modeling. And compared to previous approach, we are not just counting the number of misses. We basically are modeling a ordered set, list of set of the cache events. And basically, this enable to modeling the set associative hierarchical caches, and it also enable many practical use cases, such as bounding worst case execution time, and enable the cache vulnerability analysis, and also some determine the array padding size, and so on and so forth. And my talk is before lunch on the other room. And welcome to listen to my talk. Thank you.
Okay, let's give all of the speakers a round of applause. So as you can see, we have a great program today, and come back promptly at 10:30 for the next session.